Now, if you've gone through our last video, there must be a question nagging at the back of your head. That is, how is a slit able to turn regular light into a point source of light? How come light that's traveling through a slit bends and spreads across the screen rather than just goes straight through? The answer to this question lies in a phenomenon called diffraction. This phenomenon is pretty amazing and causes waves like light or sound to bend across corners when going through an opening or around an object. It's one of the reasons why you are able to hear people around corners even though you can't see them, and the reason why shadows appear fuzzy and blurry in certain lighting conditions. In order to understand how diffraction takes place, we need to take another look at how waves propagate. In an earlier lesson, we explained how each wavefront becomes the basis of creation of the next wavefront. For sound, that's in the form of air molecules in one wavefront pushing onwards to create another wavefront when molecules next in line. Same is the case with water waves, where water molecules at one wavefront collide with those adjacent to them to create a new wavefront. This process continues until the energy being transferred from one wavefront to another completely dissipates or is absorbed. Huygens developed an explanation for this process of propagation. He stated that each point on a wavefront passes on energy in a circular pattern. The next wavefront forms when these circular patterns meet. This is a very useful explanation when trying to visualize the way diffraction takes place when waves are passing through an opening or around an obstacle. Imagine a plane, or what we call a straight wavefront, that reaches an opening. Now, at that point, the wavefront is restricted around the edges, causing the wavelets that would form part of the next wavefront to be removed. This causes the wavefront at the edges to be curved, thereby appearing to bend around the corners. You also notice that the smaller the opening gets, the more circular the wavefront becomes. In fact, waves will diffract the most when the size of the opening is almost the same size as the wavelength of the wave. We can actually demonstrate this using a ripple tank setup, where we place a barrier with an opening that can be changed in size. You'll notice that a large opening will not diffract the water waves by much. But as you make the opening smaller and approach the wavelengths of the waves, diffraction will get larger and the resulting waves will become more and more circular. The same thing can be noticed around the corners of an obstacle. As the previous wave becomes blocked, the next one curves around the edges to bend around the corner. This is the reason why someone standing behind a wall will still be able to hear another person from the other side. Sound waves bend around the corner to reach the person. It's also the same reason why the lines around the shadow of your hand are blurred and not sharp. Light waves are bending around the edges to reach areas that are supposed to be in your hand's shadow. That is why, in Young's double slit experiment, slits were able to turn a single diffused light source into two coherent point sources, allowing the experiment to be performed in the right way. Another interesting thing about this phenomenon is that not all waves bend the same way. While you can hear sound from behind a wall, you can't see things that way. This means that while sound waves can bend and diffract around the wall to reach a person on the other side, light waves can only diffract just enough to create a fuzzy outline of the wall's shadow. This is because waves with longer wavelengths, just like sound, can diffract more than waves with shorter wavelengths, like light. This creates very interesting applications for the phenomenon. For example, if waves diffract at different angles depending on their wavelength, can we use it to separate white light into its different component wavelengths, that is, different colors? You can observe this by using a diffraction grating. A diffraction grating is essentially a screen with multiple equally spaced slits cut into it, much like a mesh or a filter. These spacing act as individual openings for light to pass through, causing light of different wavelengths to diffract slightly differently, creating a pattern of colors on the other end. This is exactly how a spectrometer works. A spectrometer is a device that can decipher different types of elements or molecules that are present in any given mixture or sample. Now, it uses a diffraction grating to separate light into its component wavelengths and then uses those wavelengths to strike the sample mixture at different angles to measure their interaction. Spectrometers are extremely useful tools for chemists, doctors, forensic scientists, and archaeologists who use it to determine the composition of different mixtures as part of their work. Does this then mean that any filter can act as a diffraction grating for light? Or does it have to be of a specific width and an opening size? Well, these are some of the questions that we'll be answering in our next lesson. So stay tuned.